Right, so this was the first few classes, this is the second few classes, and because I forgot to push record, I'm not going to go and explain it all over again for you guys. But you can see that this is all about kinetic movement, changing, just heating up, physical changes only, or cooling down. And this is about a reaction. Okay, so today's lesson is about tying these two things together. So how did, obvious question really, how did the pot of water warm up? From the flames. So there was a heat transferred from here to here. And according to some fancy law called the first law of thermodynamics, says that heat can't be destroyed or created. Right? Right. Heat cannot be created or destroyed, rather just transferred from one form to another form. So the assumptions that we said here, we're assuming there's no evaporation, we're assuming there's no state change, we're also assuming that all energy is transferred from the flames to the pot of water in this case. And that no energy is lost, no loss of energy to the surroundings, which is very ridiculous because again Zach said, well, there must have been some energy in here, which is true, really, isn't it? This air would have warmed up, right? So because it's warming up, physical change, and therefore we should have a Q equals MC delta T for this air. Would you agree with that? Right? And so we don't have a specific heat capacity for air. Actually, you do in your data booklet. If we could figure out the mass of that air, well, that's a bit trickier. And the temperature change of that air, put a thermometer there, we could figure out the Q equals MC delta T of that, right? And the pot will get warmer, won't it? So let's say the pot's made of aluminum, the MC delta T of the aluminum pot as well. And we should technically add all those things together, right? And we don't want any heat to the surroundings because we all know that. So really we should put a big container around it too. Okay, this is getting a bit ridiculous. Oh, and a lid on top of this too. Okay, this is getting a bit ridiculous, right? So there's a lot of assumptions that are made that the heat from here has been transferred into here, but we are going to make that assumption anyway. And if it has transferred 100%, you could say that the potential energy from there, making sure this is still in the counter frame, potential energy will equal the kinetic energy. You okay with that? The potential energy from here, so if this was 1,000 kilojoules outputted, the 1,000 kilojoules will be in the water. Or actually, it's much more logical to do it the other way, because I can figure out temperature change. You can figure out MC delta T quite easily, and so therefore that should tell you how much energy was released by the reaction. And if I look that up in a data booklet, I could figure out how many moles I let go of out of my pipe. Because that's the tricky thing to measure. Hi.
I remember this stuff.
Good.
It's fun. We're to have it.
Yes, of course. Okay, but this is losing energy, right? And this is gaining energy. Would you agree with that? So if we've already said that losing energy is negative delta H, then gaining energy must be positive delta H, so they're the opposites of each other. So EP equals negative EK, because they have to be the exact opposite number. If this is losing 1,000, then that has to be gaining 1,000. So we put this in arbitrary negative. And potential energy is N delta H. Everybody okay with that? And kinetic energy is this bit here, and so that equals MC delta T. Oh yeah, that little negative there. And so now I have another formula, which is a combination of the two formulas that we've used before, which then can allow me to figure out energy lost, gained from the reaction to the pot of water, whatever way I want to go, whatever little system I want to find out. I could figure out my mass, M divided by big M. I could figure out my molar enthalpy. I could figure out the mass of pot of water that I would that must have been there. I could figure out the specific, right? I could figure out any of these variables just using simple algebra. You with me? Okay. And on this booklet here, we're going to go through some of these examples. Okay, so let's look at example 1 then. Maybe if I can get this to stabilize. Okay, so over here, we'll look at example 1. Let me just zoom this up slightly. So, it sounds really easy so far, but of course, true to chemistry, it gets complicated quite quickly, okay? So, here is a styrene colorimeter, or in other words, that just means a polystyrene cup. There's a booklet for you on that desk there beside Katie. Just a polystyrene cup with a lid on it and a thermometer inside. Everybody okay? So what you did for your experiment, but with a lid on it this time. They're going to use 100 grams of sulfur. They're going to burn it in oxygen in this styrofoam cup. And they're going to produce the poisonous sulfur dioxide gas. Okay, you with me? And they would like to know the molar heat of reaction of sulfur. Now imagine how hard that is to figure out. Those delta H's have all been given to you up until now. This is how they figure them out. There's the mass of water in the styrofoam cup. There's the temperature change. And we start with this relationship. I know the negatives on the other side. It doesn't matter. I'm pretty sure your textbook has it on the EK, which is why I did that on the board. Okay? Because I thought this is the one sheet you'll see, but you'll see the textbook a lot. So I put the negative on the EK, because I think that's how they do it in the textbook. It doesn't matter which side you put the negative on, as long as it's the opposite value each time, right? Exothermic one side, endothermic the other side. So, MC delta T for the heat of the water, and N delta H for the heat of the reaction. Okay? So this is saying the sulfur is burning, all that energy is going to go into the water. And that energy is going to equal each other. Okay? I don't have an N of sulfur, I have a mass of sulfur. So, little m over big M. Sulfur is S8, so therefore I've multiplied the number on the periodic table by 8. So that's where that number comes from. So, mass of sulfur divided by big M to get my number of moles. This is what the question is asked for, molar enthalpy, equals my MC delta T. Why do I use the mass of water here and not the mass of the sulfur? Is the sulfur undergoing a kinetic change, a physical change? Right. So the sulfur is on the reaction side, the water is on the kinetic side. Do you see that? So basically, you know that line that I drew on the board over there with the reaction, like we have the flames here, the reaction line, the pot of water? This line is now just tilted. So this is the reaction, this is the water. Get it? So you have to keep them separate in your mind, otherwise you're going to end up using wrong masses for wrong places. So the water is increasing in temperature, so I use the C of the water, not the C of sulfur, and I use the M of the water. So do you remember when we were doing the experiment? I was like really big on that, wasn't I? Where's your thermometer? Where's your thermometer? That's the C we use. That's the M we use. This is why. Because pretty soon you get a couple masses, and you got to figure out which. So tappity tap tap into your calculator, times by that, divide by that, and you end up with this megajoule per mole value. Which then I could ask you to communicate that value in a variety of ways. This is using delta H notation. I could ask you to take it and put it as a term within the balanced equation. Remember that? So that would be left or right side of that arrow. The right. The right. Endothermic or exothermic reaction? Exothermic. So energy is produced. So therefore the right-hand side is a product. Or, use your algebra, negative values always get put on the right-hand side of the equal sign. If you want to express them as a positive value. Okay, and could you do an enthalpy diagram for this? Yeah? It would look like this. because it's exothermic. Okay? All right. Happy? Get it? That's as simple as it gets. Okay, here's one that's a little more complicated. Okay. So, a large sample of molten. What does molten mean? It's liquid, melted. Okay, so liquid or melted. At its melting point. Okay, so they would have looked that temperature up in your data booklets. You probably have a melting point, boiling point. I can't remember actually if you do or not, but a lot of periodic tables do. Look that value up, and I don't know. Let's say it's whatever, 200 degrees Celsius. Okay, is placed in 1 liter of water at 25 degrees Celsius. Imagine it. Imagine. It's so hot it has melted. You dunk it into this room temperature, basically water. A bathtub of, because it's 1 liter, so okay, not a bathtub. This much water. Okay? So you dunk it in this much water. What happens? What do you think you will see?
It'll bubble.
What will bubble?
The water.
Well,
It'll boil.
most likely as long as the water goes to above 100 degrees Celsius. Well, let's just keep reading. Oh, final temperature of 38. So it doesn't. Although you're right, that's what we would think would happen, because it does happen with iron, or it depends how big the block is that you're using. So what else would you see?
It would harden, molten.
Right? Would it solidify? And not only would it solidify, but it would cool down. And it cools down until they are both, that's what this means, both the piece of metal and the water reach a temperature that's the same in equilibrium. Okay? So it's the same temperature of 38.2. So you took this liquid metal, you solidified it, you cooled it down. The water warmed up a bit. Okay with that? You see the two things happening? So on my left-hand side here, I have cobalt. What's happening to the cobalt? On the right-hand side here, I have what's happening to the water. Okay? Well, the water bit's a bit easier, so let's just talk about that one for a minute. That's kinetic energy, mc delta T. Are we okay with that? The mass of the water is 1 liter or 1 kilogram. The temperature is, or the specific heat capacity is 4.19, and the temperature change ends up being 13. Okay? The cobalt. The cobalt is, first of all, solidifying. That's forming bonds, intermolecular forces, going from a liquid to a solid. Right? Your intermolecular forces are coming closer together. Do you remember this? So that, because you're breaking and forming bonds, is a potential energy. And N, this is mass divided by big M, times delta H. Okay, look at your data booklets quickly on page like 5 or whatever the list of formation reactions. And find water on there. Bottom right hand side. 4 or 5?
Liquid or vapor?
Ah, good question. Liquid or vapor. Do you see that they're both there? And do you see they have different formation values? Because you have a different type of bonds forming and breaking, whether you're forming gas or liquid. Everybody okay with that? Or solid, but solid's not in your book. So there are bonds breaking and forming there. So here's that temperature change, and here's that potential energy change. And I must say this, I don't see this very often in the syllabus anymore. This one, though, I have seen on an exam. So all day long, you're doing your delta H equals mc delta T. N delta H equals mc delta T. N delta H equals mc delta T. And then they throw this question at you. That cobalt cooled down. No reaction. No bonds breaking and forming. So what's happening to the cobalt? An mc delta T. Because, as you said, that piece of cobalt first solidifies, then cools down. Okay? So, cooling down is just MC delta T. Only here I've got the mass of the cobalt, the specific heat capacity of the cobalt, and the temperature change of the cobalt. Cobalt on the right, water on the right, left. Oh, the other way around, sorry. Okay? Tap, tap, tap in your calculator, and you find your one unknown here, which is the molar enthalpy for the change. How much energy was used to solidify your cobalt? 19.1 kilojoules. Exothermic, does that make sense? If you go from a liquid to a solid, is that going to give out energy? Is it going to cool down? Yeah. Think of it the other way around. Going from a solid to a liquid, do I have to put energy in? Going from a liquid to a solid, oh, the other way around, I said. Think of a solid to a liquid. I have to put energy into it, right? So this must be endothermic. So therefore, going from a liquid to a solid must be exothermic. And indeed, your value ended up being negative. You with me? Kind of? Okay. So the third example I'm not going to go through right now, because it's kind of another thing, and I think you guys are saturated by this point. We'll just practice this for now. So using this, oh, look at that. Okay, using this, I actually would like you to do the circled questions, but instead of doing question 8, can you do question 7? Okay? So instead of 8, because 8 involves that third example, we'll just wait on that. We'll do questions. What have I got circled up top?
1, 2, 4, 7.
Okay, so 1, 2, 4, and 7, please. Okay, 1, 2, 4, and 7.